we are starting to record now. All right, so be watching for the homework that is due before class on Thursday. We'll review on Thursday. You'll get two practice finals over the weekend, and then send me your not available times Wednesday, Thursday, Friday of next week, so we can schedule a review session, and then your final is on the 11th. All right, we'll get into our last topic, which is from Chapter 8. Chapter 8 talks about RTL design. We've already talked about a bit of this type of design already. The one big topic that is good to add in is a design style called ASM, Algorithmic State Machine. You can also use this in asynchronous design. So I've seen it also called asynchronous state machines, um, because you can have states and they don't necessarily have to be timed to a clock, although they often are. Um, I think algorithmic state machine is kind of the more general title to it. So I'm going to stick here to algorithmic state machine. The idea behind an algorithmic state machine is basically what we used to call flowcharts. So flowcharts basically are made up of a series of states and then decisions you can make and actions you can do as a result of them that then lead to the next state. So the basic elements inside them is we have these square blocks, which are the state blocks. Usually the state name goes here on kind of the upper left-hand side. And then inside anything that automatically happens. So if we set variables, if we set outputs, the second you're inside that state, they all go inside here. You just list them. You can make the box as big as you need to accommodate whatever those actions are. If there's a huge number of them, it might be good to just kind of list, a particular some type of configuration, and then somewhere else have, all these outputs are part of this configuration. But, that's just kind of time-saving shorthand. But the basic idea is you have the state, and inside here you have the actions, and you'll have arrows that lead in and out. By default, as soon as this state has completed, which in our case will be as soon as the clock cycle comes, it will be out of this state. It'll be to whatever the next state is in our action. Now, so this is one set of things. These are called state blocks. There are also decision blocks. Which look like diamonds. And very often what we will test is just a single variable or value, right? So we might, test variable X. Sometimes people will put a question mark after it. And it will have two things that come out. It could come out the bottom and fork, in which case you would list the values, true, false, to say, is X true or false? So there'll be one out for every possible thing that could be on here, right? So I could have true, false. In this way, where it comes out the bottom, I can also have my decision blocks go out the sides, where I would label them T, F. Inside, in addition to X, I could have any statement. So this is anything that you can test. So I could, if X wasn't a Boolean, if X was, an integer or a float, I could ask questions like, is X bigger than 5? As my question inside. That would also be completely legitimate. Anything you can do for an if statement or for a case statement. Either one, legit to put inside here. Um, if it is something for a case statement where there's a whole bunch, we tend to do this bottom style because this bottom style, like let's say x was an integer and it could take the value 0, 1, I could just keep cascading them out, right? 2, 3, right? So for case statements, you almost always use this style, which is a little newer, where it has multiple drops that come off it, and therefore this kind of drop bar is part of the statement. The original style, you went out left or right, and it was really for doing Boolean tests because it was originally this was only for if thens. But typically, when you see this, you tend to think of an if then type structure. When you see this, particularly with multiple drops, you tend to think a case structure for implementing. Now, if you've got some complicated statement in here, this can get really, really difficult. You can imagine, the board's small here, but imagine I have some crazy large statement, you know, x squared plus 3x, minus 2x is greater than 5. Right? You can get a lot of wasted space above and below in these. So to account for these really long statements, in addition to the diamond, we also allow these kind of truncated ones where it looks like kind of a rectangle with pointy ends on it. But it's really a truncated diamond of what we've done, where we just cut it off and things come in and go out and left. And you can still do the same usual, come out the left and right for a true false, or come out the bottom and have a bunch of drops in the case of a case statement. So this is, if you ever see this shape, it's no different than these. It's just a space saver. When you had really small variables, you didn't need to worry about it. But when you get either large variable names or more complicated expressions, I'll go. Oh, I see a question that's in here. Will the final be like the homework? The final will include questions from the beginning and questions that will be somewhat like the that homework that you're going to be doing that I will release tonight. So again, when you're doing that homework, you are practicing some stuff for the final because there's really a few key topics that we have covered since then that are good testable material. How do you design using flip-flops? How do you analyze using flip-flops? How do you design with counters? Registers, and how do I do shift registers versus parallel registers and their arithmetic? There's a few key topics like that that are very testable. There's some stuff like the Chapter 7 material, which is good knowledge and allows you to actually do designs a little bit better. But that's kind of more helpful towards what I would call the lab aspect. Then it's not necessarily quite as easy to check. If you understand how things work, it's kind of easy to do that. The stuff today will also be very testable type stuff, which is why I wanted to kind of rush things up so I got through this and time for you to kind of be able to test it, because ASMs are actually one of the easiest ways to write Verilog code from. You can almost just look at the thing and write them, and very complicated designs can be made very, very simple by ASMs. So they're a really great way to handle large designs. So there will be somewhat of a similarity between the final and that homework. But again, I'm not guaranteeing that it's just going to be a rewrite of the questions, but questions that I put on the homework are questions I would be perfectly happy putting on final, if that addresses it, Jordan. Awesome. All right. Do we feel good so far with the first two types of blocks? State blocks that do things, and decision blocks which let me test them and branch. after any of these, I could immediately go to my next state, or there could be some things that I conditionally do inside my state. So we have a couple more blocks. I'm going to erase these so that I have enough room. So we also have conditional blocks, which kind of look, I always call them lozenges. I don't know what other people call them. They kind of look like there's really large pills you sometimes have to take from the doctor, rounded on the ends, but it's a rectangle, but they're completely rounded on the end. These are conditional blocks. Like a state, you can put any statement that needs to happen inside here. So these can stretch down and become big. You get large rounded ends. Um, but you can have as many of these as you want, but they must follow one of those decision blocks. Right? They don't make their own state, so there's no state that's mentioned up here. Um, whatever is here is part of the state block that's most immediately before it. So these ones typically you'll have a state block, and then you'll have some type of a decision, and this conditional block will be part of this state. And it will happen in this time period because this state, and it will go down, and then there'll be some other state that will follow. I'd say state two. Right? Everything from here up above is part of state one. So state one includes some of these unconditional statements, a decision block, and some conditional statements. And then a new state happens as a result. Does that make sense? So for a basic one, this is all you need. I think this is all the book talks about. There really is one more, which are these circles. And these ones are used for start, stop, and jump. Imagine you had a really big flow chart. Right? I'm going to start with the jump parts here. If I had a gigantic, um, flow chart, it might not fit on one page. It's really easy not to fit on my whiteboard, but it might not fit on my page. So I could, for instance, if it was going to go past whatever I'm drawing the flow chart on, and I need to use a second page, how do I move from one spot to another? Well, maybe on this S, 2 over here, I might need it to go, um, this state is done. It's real simple. There's no condition to it. It just automatically goes, um, you know, do some whatever, location 5 or something. And then somewhere else, I would have a location 5 and it would pick up. So this is just basically doing a jump from one spot to another. It's part of start and stop because this is where L5 starts and this was whatever the previous thing was stopped. So these are kind of, if you think about them, these are your begin end for any given set of these. So you can nicely break these into, procedures and functions and other things by setting up, I could call, this by some procedure name, and I do whatever the procedure is I want to do, and then I could have, whatever my return statement or whatever I want that comes back, what destination should I jump back to go back to my main. Right? So these ones allow me to kind of break things out and to do that kind of programming structure, which is really designed to break things up into pieces. So that's what the circles do. They can have labels inside them. If they don't have labels inside them, they're start stops. Usually you also put a second link around for your start stops to tell you, it just makes it a little easier to see. But that's not a universal convention. But it is a fairly common convention. So I think a lot of computer scientists, for instance, these ASM charts are used in computer science all the time too. They are there. They're called flow charts. They also have a version of these flow charts in UML, which is all computer science. But these are the four basic blocks, right? A state block, a decision block, a conditional block, and the start start jump notations. All right. Do we feel good with the basic ideas of what's here? Okay, I'm seeing some yeses come in. Awesome. So let's actually make one. So let's take a fairly simple little example that we might want to do. Um, let's say, for instance, um, I wanted to have a, um, let's say I want to build a bus monitor, right? So this is a little more complicated than what you built before, but it'll be surprisingly simple, right? A bus is a communication device and allows you to transfer data between them. Um, let's say that I am going to be building some device that's going to hang off of a bus. It's not the computer, so it's not the bus master. It's just one of the devices that hangs on the bus. So it needs to look and see, is anybody talking to me? It needs to monitor the bus and say, is something coming to me? And then if it is, it needs to act accordingly. So we're going to have a bus monitor. And that bus monitor needs to do some things. The bus, maybe we'll call it bus as its variable name. So this will be maybe we'll say dbus for the data line of the bus. Right? Now, for my particular thing, I could have an idle state where I'm just waiting around, wanting to hear, is anybody talking to me? Right? So what do I do in this idle state? Well, I'm not going to do anything by default. What I want to do is actually check to see, right, if the data on the bus is actual real data, right? So normally the bus will be Z if there's nothing there. There's no assertion. But if there's a 0 or a 1, it goes high or low, um, then I know, hey, some new data is coming in. Very often, to make it easy, there's a convention that you have to start your thing with either a 0 or a 1 or some combinations of 0 or 1 to tell everybody, hey, wake up. So I could, for instance, check to see if, let's say, my convention was that, if data bus gets a 1, then somebody's telling somebody to do something. So I've got a 1 in all other cases. So we use an asterisk to mean anything else. If data bus is equal to 1, you're going to come through. In all other cases, nobody's trying to get me. So my next state's going to return right back to idle. And you're just going to keep waiting until you see a 1 appear on this bus after it's all done. If it was a 1, then I'm going to go to my next piece of information. And usually after it gives that initial kind of, here's a signal to you, it'll give you information about who it is, right? Who it's looking for. So the next state is kind of our address check. So I might call that state address. And I can see whether data bus, right, is equal to whatever my address is, which maybe I store it in ADD, right? So meaning ADD is some constant, which is my local address. And if the data bus ends up giving me my address, then I go, yay, great, right? So I shouldn't do that here. I should actually come down and see a little bit bigger than that. I want to know if data bus is equal to my address. So again, a decision block. And it's either yes, it is, or no, it's not. If it's not, I'm going to go back up. Right? If it is, then I need to go to a new state, which is going to be my get data. Get the data off the bus. Right? And so, for instance, maybe I set my output, and let's say my output is X. I can set X to be equal to the data that is now on the bus. So I read the data that was sent to me. And after I read the data, let's just say it sends a single bus width worth of data. Once it's done, I'm automatically going to go back up to my idle state. This is a very simple bus, but it is a bus that can work. I've got an idle state. I wait for data. I check to see if it's me it's talking to. If it is me, I collect the data they send, and I come back up. So it kind of expects this signal of, database as all ones, or data bus as all ones, to say wake up, address, right? Check to see if my address is the next piece of data that's on it, right? Collect data if it is. So does that make sense as a description to you? So somebody could easily tell me that piece of thing, right? There's kind of three states to it: a wait state, check your address, get your data, return to wait state. This is not too different than most of the buses. It's a little simpler, but it's not a lot simpler than buses you'll see on a computer. For instance, this address and data aspect here is exactly what takes place, for instance, on the memory bus inside your computer. These have become very wide buses. These buses are usually 64 bits wide or so. And often the address and the actual data are sent in parallel. So there's often, say, like, you know, 32 or 40 bits that are dedicated to the address, and then there are 64 bits dedicated here, then some control bits. And the total mess is like 128 bits coming across. And I do it all in one cycle. So for, really fast buses, we give you more wires so you can take less cycles. For slower buses, like, a USB or an I2C or things of that sort, we tend to do this: send the address, send the data on the same data line, because their speed is not as important, right? But we do care about number of wires becomes more important. So this is actually, for a simple design, it's pretty easy to go. Does that make sense? Awesome. So let's talk about, now I've been able to take a word description and put it into a very nice, easy, um, kind of flowchart setup using my ASM. Now the question is, can I turn this into very nice and easily some code? I'm going to do one simplification here. I'm just going to take this and go here. Just meaning it goes to here, which goes to there, which goes to there. It just gives me a little more room on my cramped white. If I was thinking from all on the other side, because that would have saved me even more room. But I'm going to kind of put my code over here. Now, I've got three different states. So I look at this and I go, three different states. Now I can pick what matters to me for my addressing style. You have to do everything we've done before. Because converting from this is exactly equivalent to all the other things we've built. Right? So the state diagrams, the logic diagrams, state tables, all the rest of that, ASMs are also equivalent. So we just have to convert from this to those. We look at this and we go, okay, what are my inputs? Well, my input is, for instance, data bus. That's coming from the outside world. I'm going to create a module, which is my bus reader, and it's got input, and I'm going to say that I have 8 bits here. That means 7 down to 0 zero of D bus. So I've got, you know, basically 8 bits on this data bus that I can read in, and my output is going to be X. X is the data that I'm sending to the rest of my local device. My whole job here is just to do the bus read. So my output is also 7 down to 0, and it's my X, the data that I read. So I can look at this and I can see, you know, things that I'm sending out and things that I'm reading and using internally to determine what their function is inside my module. So that's step 1. I kind of determine my inputs and my outputs. Now I can look and say, what are the internal variables that I need? Well, internally, I need to have a state to track which one of these. So I've got to determine, do I want to use binary? Do I want to use gray code? Do I want to use one hot? Let's say I want something very small, but I do worry about errors on flipping. So if I'm concerned at keeping things as small as possible, and I am worried about error stuff, I might decide to pick gray code as my transition. So that means my state I need to say what it is. It's a reg 1 to 0 because I need 2 bits for gray code to have 3 different things. State and next state. So I've now got my 2 bits set up for those. I know I want to do them gray code. So to make my life easy, I'm going to actually set my states as parameters. By convention, parameters should be all capitals. So again, convention doesn't mean it's required. Convention means that's what everybody's going to expect, and if you follow that, your code is readable and self-documented. Right? So by putting it in all caps, I'm telling people it's some type of a constant, which is usually set by parameters. So I say parameter idle, and this one I'm going to set to be equal to 2 bits, binary, 0, 0. That'll be my idle state. And then I'll have parameter address. And that's going to be equal to 2 bits, binary 01. And then I'll have a parameter get underscore data, which get data will be 2 bits, binary 1, 1. Follow the gray code standard. Okay? And this way I won't have anybody flipping in any kind of odd order. Now, if I'm being really, really careful, I might make a state in between this one and this one that'll just take one extra cycle because you're not really going to, immediately after this data, there has to be at least one cycle of nothing to separate the next data bit that's coming in. So I might make a parameter wait state, which would be 1, 0. I'm not going to worry about that here. I just kind of mention that if I wanted to make this even nicer. But right now I've got my state set up, and now I can just use these names. I don't need to worry about what I picked or what the convention was. The parameters are now going to enforce it. I just need to remember these names. Now, sometimes when people pick these, they'll put on the opposite corner the binary pattern that reads them. So if you ever see a binary pattern written out there, if it's written over here, it is the name. If it's over here, it's the particular one they chose for it. So address is 01. Address is 01. sometimes you'll see it, sometimes they won't, right? Um, does it make a difference between parameter and local parameter? So yes, there is a difference between parameter and local parameter. I wasn't really emphasizing the difference. Local param is specifically for internal. Um, param technically exists in a bigger sense that's outside. The real difference between them is a parameter can technically be set before you enter the module. So let's say I pick these as parameters here, and I go on and I build mine, and later down the line, somebody determines, oh man, his choice of parameters, while it made sense to him, is a really bad choice given this other piece of information he had no name of. They don't want to modify my file, but they want to be able to change my choice of values. Um, Prior to entering the module, you can actually, for parameters, you can override parameters that are declared inside. So Verilog gives you a methodology. I don't want you to worry about it now. It's something we deal with in advanced digital logic, but it does allow you to override parameter values. Local parameters, you don't. So local params are completely internal, so they're theoretically protected from somebody ever making those changes. So I would pick a local param if I don't want them to be able to override. I would pick a param if I wanted them to be able to override my choice, because I just kind of picked it for my own usage, what made sense, and they might say, no, 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 I don't like that usage, I want to override. So that's really the difference between param and local param, is whether somebody external can change it. So I'm leaving it open for people outside to change it, because I'm saying this is not the end of the world to me, as long as you do it consistently. And modifying here, it'll consistently change it all the way through. Awesome. Okay, we feel good through this. Okay, if that feels good, the only other one here is this address, which again, I'm going to set a parameter, and I call this one address, which is equal to the default address that I'm going to get named on the bus, which I'm going to say is 001. Now, I haven't put a binary on here. By putting 001, it's actually no difference than writing 1. But what I've suggested to you by this kind of a numbering system on here is that I'm allowing it to be, this is in decimal, that I'm saying there could be up to 1,000 devices on here maximum. And by default, I'm going to ask for location 1 if I can have it. Again, I make it a parameter because at that runtime, somebody might overrule me. They might have put some other things on the bus, and they might want to say, yeah, you want to be 1, but you're actually number 5. So they would allow me to then, I've picked a default and I'm letting them change them. I could also do the same type of thing in here as a parameter that's passed to me as a bus name. I did it for just because it kind of fits in with the rest of the scheme. It allows you to modify, but that would have been an equally valid choice to do a parameters. So now I've got one's add. I've taken care of it with a default value. I've got each of my state values set in here, and I've handled my inputs and my outputs. So now all I have to do is create the necessary register file and then do the next state logic from it. So far, so good. Awesome. If it's okay, then I'm going to erase this because I'm out of room, but you've got it. I am recording it. It says it's recording anyway. This would be a good time if you want to take a picture of the screen too, so you have it for your reference, because it'll be like a day till this shows up. Sorry, that's just how slow it is. I will check tonight when I upload the homework assignment, homework quote unquote test. But or two for you to take a photo. Okay, I'm presuming you could have taken a photo in this time. If not, put in the chat window and maybe somebody who has is willing to share one. Or you can just wait till the thing appears. So assume all of this is here. Now the first thing we want to do is we're going to create our memory. Now you could integrate the memory and everything else, but I tend to like to stick with the thing where I've got my memory and it goes my next state logic that feeds back into memory and inputs and any out logic I need and the outputs. So I tend to like to stick to this pattern because it's a very, it's a safe pattern. So I'm going to build the memory first. And all I need for memory is to hold which of the addresses. So that's going to be, this one is a flip-flop. I need always at, and I didn't put this in, but I should have. Pause edge of the clock. Right now I just have clock. I'm not doing reset. I could, if I wanted, I could also have neg edge reset. So I would have to add, obviously, clock and reset as single bit wires coming in as inputs. I should have thought of it when I was doing it, but I honestly did. But at this point, I would then go up, modify the module to allow my clock and reset come in to handle. If you're doing system verilog, I have noticed a few people have done it. You would have always underscore FF for flip-flop, which specifies, yes, I really do want memory. It will be inferred from the pause edge clock for a regular verilog. Since I have a reset, I'm doing neg edge. I would then check to see if not reset. So if not reset, and put in parentheses to be very careful. Then I would say, whatever I called my state, I think I just called it state. State gets the value of 0, right? Now the best way to do this is instead of 0, since I have it, I'm going to say, I want the state to go to idle. That way I can now specify. If somebody does a reset, I want to go back to idle and wait for the next +1 to start up. That way, if somebody renumbers idle to start some other place other than 0, they can. 0 is, in my opinion, the best spot to start. But for instance, Intel doesn't start their computers at address 0. So, go figure. Sometimes people don't use 0, so it is a little safer to do this for the reset. On a reset, go to the idle state. That way, also, when the computer starts up, you can send that reset call through and you know it's now in the idle wait state. It's actually a strike. Else, right, if it's not a reset, right, then it must be a regular operation, which means state should get next state. And that is everything I need for my memory. This is going to look almost identical every time you generate it. That's why I say part of this is so easy. You're guaranteed one of the more complex things, it's easy to tell. The other advantage of this, if these get large, your states, you get more bits, there are blocks. We talked about how the basic logic blocks have a flip-flop in them, and I can stick those flip-flops together to make memory. They also have memory blocks inside. So if I have larger pieces of memory, if you follow a very standard memory template every time you access memory, it can allow it to know what type of resource to pick. And it would say, oh, this is only a memory action. I can pick one of these memory blocks instead of picking a logic block. But depending on what resources it has available, following a convention like this just makes it easier for the system to infer what type of thing you're trying to build. So it'll pick the resources better automatically. That just gives you a better design. All right. We feel good with that? Yay. Um, let me do, in this case, my output logic. I'll just make a comment. There's no real output logic that I'm having to deal with. My output's going to be set here, and it's just, output is just getting a value. I'm never looking at it. I don't check the data. So I don't need to do anything funny for this. So I don't need any output logic. If I'm going to be checking it, I might make another internal variable, double X or something that I could check to, and my output logic would be like assign X equals double X. Remember, if you've got output logic, you really should never read it, i.e. it should never be on the right-hand side of an expression. It should only be on the left-hand side. And it should never be I should not ever have a case, everything inside here, both left and right in a decision block, are reads. So I should only have writes. So it should only be on the left-hand side for an output of either a state or a conditional block. It should never be on the right of a state or conditional, and it should never be on either side of a decision. In this case, it's only on the left, so I'm good. So I don't need to do anything special here. So the only thing left is this next state logic. I'm going to erase this because it's going to take the whole space for my next state logic. So I'll give you a sec here to take a photo of this. I guess since you're taking a photo, maybe I should put a note. Add input block and reset to the module since I added them here. Give you a sec for pictures. All right. Hopefully that should be enough. Now we're going to do the last one, the next state logic. I don't need that picture down there either. All right. So this one is going to be my next state logic. It is combinational. So always add star. Now in this case, it's going to be very simple. I'm going to use a case statement. Case my state, and then I can say for idle. And what do I want to do inside idle? Now I can just look at idle. And idle is this part here, well, including that one. I can see I don't set it here. The only thing that's happening in idle is this check. So I can then say, okay, inside idle, all I'm doing is if dbus is equal to 1. If dbus is equal to 1, then my next state is equal to address. Else, my next state is still idle. So we can see this is just an if statement. So I replace it with an if. Whatever's inside is the thing I have to check. I say, am I going to this one? In which case, my next state is address, or am I doing everything else, which means it just loops back around. So I could turn this picture into code in an instant. Idle, boom, do that if statement. If I had any automatically occurring statements, I would just have a begin and an end, and I do it before the end. You literally can just begin, write everything here, and then put the if statement, and then end at the end of it. In this case, I only had one statement because I only had that. Does that make sense? Awesome. So you can see it's actually pretty simple. Everything here, I just took this block and moved it over. I'm going to pick another color here. My next state is address. That is this whole lovely thing. So I look in here, there's no commands inside my address area. All I have, again, is one of these conditional blocks. So I can say, if I look at the statements that's in there, the data bus is equal to whatever the value of my address is. Well, if it is, then my next state is get data. So if that is true, next state is equal to get data, semicolon. I put this on the next line, that's a little scrunched. All right. So again, all I did, I take the address, colon, and then I only have one statement. I take whatever's here, that goes inside what the if statement is checking, and if that's true, I give it state. If it's not true, else, that's the other line coming out. The next state is idle. All right? And again, I use my names all the way through. Now, if you noticed, when I was doing the flip-flop, I was using my non-blocking assignment. Inside my combinational one, I'm using blocking. Um, it's just a safer convention. There is a couple cases that you can run into problems if you don't follow this convention. If you follow this convention, you're pretty much always safe. So this is designed to be a very safe convention. So just think, if it's a flip-flop, use non-blocking. If it's combinational, use blocking. That's the basic rule whenever you're dealing with it. So you notice I'm following the convention all the way. Right. But I've now got, again, there's only one statement, one if statement inside address. I grab the purple again. Let's see. Try green. I've got one final one to do, which is get data, which is right here. There is no conditional clause on this one. There's just, an unconditional. So I can say, hey, if I'm in get data, I'm going to have two statements. I'm going to have to assign X, and I'm going to have to assign next state. So I need to begin, and I need to say my output X is equal to whatever's on data bus, and my next state is equal to idle. because that's where the arrow leads. And then I end, and I am now done. I've done all of my addresses so that I can end my case. And that's also the end of my always, but I only have one statement in there, so I didn't need to begin with the always. That also finishes everything for now for my next state logic. It also has set my output, so everything was able to be handled in one little nice clean conditional block. Okay, does that make sense to people? So if you notice, algorithmic state machines are an extremely nice way to do design, right? They allow me to have, take a very complex thing. Like if I had told you, hey, look, design a bus reader inside of digital logic at the start of today, you probably would have been like, no way on earth can I do that. Well, it turned out to be a fairly simple thing. I could write it up here, condensing the ideas of them, and then it's really simple to turn it into these case statements. Whenever you do it, you will always want to do these as case statements. It's just, they're so much easier. And then for each one of these, you just kind of break the sections up according to what are the states, and you describe what the states are for each one. Then you're in one and only one state, so it just walks through. So it's a really nice way to be able to implement all of these. You can do a very similar thing with the state diagrams, the bubbles we've drawn. It's just, they don't necessarily have all the data written in, because the bubbles are small. You don't necessarily have all the statements written out. So it's often nicer to take those, turn it into this format so you can explicitly write out everything that has to happen. And then you can convert them. All right. Do we feel good with this? Could you please repeat why you put a begin and end on the get data? Yes, because there are two statements in here. X equals data bus, and next state equals idle. So just like in C, if you were writing in C and you were inside an if statement or a switch case, they call them switch cases, not case. If you're inside any of those statements, inside a for loop, one statement always automatically is assumed the next statement to be inside whatever that structure is. If you've got more than one, it assumes that it's not the case, right? So it would assume this was inside get data and this is something else, and it's going to get confused. So it may seem obvious to you that it should know that's in there, but it won't. That's the convention inside, and Verilog copies C. So that's why I always refer you back to C, so that you start thinking Verilog is much like C, because that's really the idea behind it. So this one has two statements. However, this one has an if statement. And the if statement includes one statement in each clause. So if and else is one thing, and they each get one statement inside there. So if clause gets this, else clause gets this. So this, as big as it is technically one statement. On the idle, I've got an if, and this is single one is in it's the if then. The else also gets one statement. So again, this is one statement. Since I've got two statements, assign the value of x, assign the value of x state. Those are two statements. I need a begin end, which is like open and close curly brackets. All right. I see that made sense. Are we all good? So let me ask you, this technically is correct. Is there anything you would add to this to make it better? I ask that because there is something better you can add to this. This is technically correct, but you'll get some warning. Anybody got an idea what would be a good thing to add on? Default, exactly. Awesome. Right? So it would be a good idea because I've really taken the 0, 0, the 0, 1, and the 1, 1. I haven't done anything with the 1, 0. So what happens if I go there? Right? It's not likely, but it is theoretically possible, right? If somebody's, if I'm in like the 1, 1 state and, somebody jiggles the power or something, it's possible that the lead bit doesn't turn off, but the other one does, right? Weird things happen. Sometimes there's accidents and setting things. What does it do when it gets there? Well, since it's not assigned, you have no idea what happens when it gets there, right? The machine was told, don't worry about it. It's like, uh-oh, I'm worried about this, but I'll do what you say. It'll just give you a warning. That's what a warning means. I'm worried about this, but I'll do it anyway because you told me. Um, so what I really should do to remove that possibility is to add a default. What should I put in the default? Right, so remember this, in this default case, I can only get there if I'm not in a legitimate state. So by definition, I'm in a bad place. There's a few reasonable things to do. Um, one simple one, then some more complicated ones, but all of them justifiable. Anybody got an idea what they might want to do under this default case? Next state equals idle. Yeah, that is the simple. That's kind of like the automatic, just reset the whole thing and start it. And that's what I figured would be a good choice in this case. Because I've got a simple example, so why get overly flued in on it? So next state equals idle. If you get to an error state, just restart the whole thing and away you go. That's kind of a nice thing. That is what I would do in this for most conditions. It's just walk through and do that, and I can just end my case. There's only one statement in there, so I'm plenty good. Um, so that would be a good way. Return back, and away we go. Um, can anybody think of some other things you might want to do if we didn't do that? One thing I might want to do is to go into an I could do a reset equals one. That is another good way to do it. Um, the reset usually comes out, but I could send a request to the master saying, I've had an error. Can you send me a reset? Okay? Um, and that actually allows the master to determine what it wants to do under those cases. Um, so, um, or I could request immediately on a local thing a reset, although it's usually better to make a request of the top one. Hey, look, I'd like to have a reset. You usually do that if there's a lot of voice error on the bus. And you might want to do that just to let the bus master know there's a lot of noise. If there's a lot of noise, you might want to alter things to go to a slower speed. You don't have to go to any fancy configuration. If you slow the speed down on the system, it slows the clock down. Um, Longer pulses that are sent out tend to be more noise resilient. So you're more likely to get a good signal at that. So if you've got a clock bus, which a lot of these are, slowing it down allows it to travel a little further and be a little more noise resilient. So that is another possibility you could do. So sending that request of to the master, hey, I need a reset because of noisy reads, um, would actually let the master do something, slow the transmitted bus clock to all of you, which from our perspective, your master computer is running on a main clock, but it's got, when it makes that the sub clock for the rest of the systems going out, it just does a counter, so it gives a slower clock out. It would just increase the size that it counts on, so it gets a good one. So asking reset equals one would be another good one to go on. Um, Other options I could do an internal check, right? Um, so I might inside here before I go back to next state idle, I might have what's called a built-in self-test, built-in self-test, BIST for short, right? But a built-in self-test, I might go, uh-oh, I ended up in a weird state. Could there be something wrong with my hardware? I should check this for you before going back to my idle state. So I might run the built-in self-test to just see, because there could be something that could be fixable. Right? And I would run the built-in self-test and then go back to idle. That would kind of be a nicer version. So I might want to do some amount of testing or checking if I end up at these kind of weird states. All right, is that good? Awesome. All right, so we're like 2 minutes from our time. So um, I'll leave the last 2 minutes if anybody has any open questions for me. All right, well, not seeing any questions then. Um, we'll call ourselves done a minute and a half early, or a minute and 15 minutes early. It looks like on the recorder. Um, so have a good day. Watch tonight for those homeworks. Try to treat it like a test. Um, it'll be. Can I do a quick recap for the homework? Yeah, that's actually what I'm doing right now. So watch for that homework. Um, Treat it kind of like a test. So you know, give yourself 2 hours to do it in. This will only be for the stuff since the midterm. So it'll be a little more heavy on it than the final would actually be. Um, but try to do it within 2 hours. If you do need a little more time, just give me a note. Um, so you can tell me, hey, look, this actually took me 3 hours or whatever. Um, for anybody who has an accommodation, a little more heavy on it than the final would actually be. Um, but try to do it within 2 hours. If you do need a little more time, just give me a note. So you can tell me, hey, look, this actually took me 3 hours or whatever. Um, for anybody who has an accommodation, whether it's 50% or two times more, automatically just give yourself the accommodation. You're in charge of the time. But again, note to me if you have to go past it, so like if you've got a 50% time extra, you've got 3 hours. If you go past 3 hours, tell me how much past your time it was. Same thing for double time. It'd be 4 hours. Anything past 4 hours, let me know. All right. So whatever your time is, including any accommodations, um, try to take it in that time. I will not mark you off if you go beyond time. I want to know that timing because I'm going to use it to help me calibrate my timing for your actual final. That lets me kind of know, so I know about how long it takes most people to solve problems. So that'll help me to do a better job of timing things to have problems correct for you. So there's no disadvantage on this one for doing it otherwise. I would like you to try to do it just with books and note cards. So you're welcome to use both, um, but try not to consult one another if possible when going through this. Um, it, again, that just gives you more of a test-like simulation that's in there. Um, and I'm going to use something that's a low checkbox. I only use books and cards. I that that's going to it. It should be fairly straightforward. Um, you know, um, I'll give you an out. If you had to use other stuff, I'll let you sign saying, I needed to ask some help. You can ask me help for free. I will try to get some, be available at various times throughout, and I'll post under the discussion section. So I'll open up a discussion section that has Q&A for this, and I'll try to watch it during the day. I can't watch it all the time, but I'll try to do my best for it for watching. And if I see a question come in, I will I will answer and give hints towards them. And you are welcome to look at hints that have come in that section. So that's kind of the homework as a practice test. Here at the beginning. So it's kind of a homework. So I got a question. What's the format going to be? It's going to be a kind of like a homework test. I will upload a PDF that has the problems on it. You are going to do them on a separate sheet of paper, and then you are going to, whether you scan it or take a clean, readable photograph, I don't care what, similar to what I did on your midterms, let you see them. We'll have a spot where you can upload them. So whether you want to print out the things or you just want to leave the PDFs on the screen and just write, please try to be neat, indicate, like problem number and box of solution. So it's easier for me to find them. When you take the photos or scans at the end, just look at them to make sure they're readable. There are some times the resolution ends up being kind of messed up. So as you can see, over 50-year-old eyes, so please make my life easy. Make it clean and readable, or at least zoomable so I can blow it up to be able to read stuff. You've got time and space to do what you need on those. And you'll upload those pictures. They have to be uploaded before next class. The next class, Thursday, if you can have it done by noon, what I plan to do for next class Thursday is to just walk through the homework assignment that you just did. So we'll go through and we'll do everything. You will then have a complete set of solutions with explanation. If you need to go back and write your own explanations on top of it, don't just regurgitate what I did, but process it and write your take on what I said. Right? That's what I really care about on any of the homework corrections is your understanding. I actually like it written in your style. That means I know you've kind of learned it. So you will be allowed to do the makeups on that, but you must have submitted things by noon. If you haven't submitted them by noon, then I'm not going to take the corrections because then you could have just copied them. So I will not be happy if you hand things in by the time class starts. So that'll be that. Then over the weekend, I'm going to upload practice exams with solutions for the final. And I need all of you to send me when you are not available next week, Wednesday, Thursday, Friday, so I can find the times when everybody is available. And it's much easier if you send me when you're not available, because when people say when they are available, they tend to list less times. So I need to know a specific times you're not available. Right? That is kind of the minimum set. I'll try to find a time period when everybody's free for at least 2 hours, and we'll do a Q&A session, or I'll just sit around and answer questions. And then your test is May 11th. I think everybody said it was 9 o'clock, but it's whatever it says in the regular scheduled time. And I will release it at that point, and then 2 hours later, or your accommodation time later, I will have you send it back to me. So I'll release them all at that time, and then I get a timestamp when you submit. And I can see as long as your timestamp is within the time period allotted to you. So if you have no accommodation, it's 2 hours. If you have 50% time, if your timestamp is within 3 hours, then I'll take it. If your accommodation is double time, you've got 4 hours. Right? I'll take whatever your accommodation is. If you go past that time to upload, start deducting points. So I'll want them in. There'll be a little signature saying not cheat. But I would love to be able to trust you, so I'm just going to have you, put your honesty on the line there. All right. Any questions on that? All right. I'm not seeing any other questions. Awesome. Have a great day. Sorry the semester ended up this way. It's a lot more fun for me when I get to sit and talk with all of you too. So I hope you are all doing well and your families are doing well. I will see you on Thursday for our first of our kind of practices. Um, and hopefully lab and that's going well. Wish you all the best. God bless.